8:45.
Okay, well, we're going to get started. Thank you, everyone, for joining us tonight. We're glad that you're here. For those of you who are here in person, we're glad that you're here in embodied form. If you are with us online, we're glad that you are still participating from a remote distance. We encourage you to engage in the chat window in Zoom. Steve Pauls will be on Zoom as well, so he's sort of a hybrid participant tonight. So he'll be participating in the chat and engaging there. Just want to thank you again for joining us tonight here at the Ames Center for the third talk in our fall colloquium series, which is Moving, Making, and Meaning. Again, this series, if you've attended some of our other talks, you'll know that we're devoting this series to perspectives on teaching and on learning that emphasize the core role that human activity plays in these domains. So through a variety of talks, we're examining how activities like moving or making contribute to cross-disciplinary engagement in mathematics, science, and the arts. So tonight we get to hear from Alexandria Hansen. Ali is Assistant Professor of Science Teacher Education at Fresno State University. She earned her BS in Biology from UC Irvine, her MA and PhD in Science Education from UC Santa Barbara. She also has a secondary science teaching credential from Loyola Marymount in LA, where she taught middle school science and mathematics for several years in underserved schools, motivated by the vision of equitable and accessible STEM education for all students. Her research broadly investigates how to support teachers in designing and facilitating creative and authentic STEM learning experiences that appeal to a diverse group of learners. So tonight, Ali presents her talk, Reimagining Science Teacher Education, Creating Expanded Learning Ecologies Through Community Engagement and Research Practice Partnerships. In this talk, Ali will share examples from her research in formal and informal spaces to highlight ways that we can reimagine science teacher education for today's modern world. So, Ali, thank you for joining us.
Great, thank you, Paul. Hello, everyone. How are y'all doing tonight? Good, good. Well, I'm excited to be here. Thank you for the opportunity. And as Paul mentioned, today I'll be talking about my work. And I put teacher in parentheses up here because I think a lot of what I'm going to be sharing today is applicable just to science education or STEM education more broadly, but I'll be talking about through the lens of teachers, since most of what I do is work with teachers. So we're going to start with a little thought experiment, if you don't mind. I'd like you all to imagine the year's 2035. What do you think is going to be the same about today versus this year? What do you think is going to be different? And what do you think are going to be the world's most pressing problems? So I'll give you just some time, quiet time to think through on your own. And if you've got a few ideas, maybe buddy up with an elbow buddy, somebody next to you. You want to go ahead and share anything at all you talked about or you thought about. What might be the same or different? Pressing challenges. Might have to turn around to find a buddy. Welcome. Okay, folks, do I have any brave volunteers who maybe want to share out a thought or two? Something that might be the same or different? Something that you expect our world to be facing? A problem, a challenge? Could be something your partner said.
Central Valley's going to be struggling with water.
Water. Mm-hmm. Yeah, water, environmental issues. Anybody else talk about environmental issues? Maybe. Okay. Any other challenges you anticipate you're going to have to address by the year 2035 rolls around? Air pollution, health concerns, yeah, again, connected to the environment.
Social interaction.
Ooh, say more.
Well, right now, kids especially are stuck on their phones. They don't have that human interaction, which actually creates good connections, and they're lacking. And they know they're lacking, or they feel that they're lacking. They just don't know what it is that they're lacking. I think it could get worse.
Yeah. As technology increases, permeates every aspect of our lives. Okay, great. Any other final thoughts before we move on from this question? Yes, absolutely. Going to be parents. And I'd like you to shift your attention to this photo here. The people who will be graduating from college in the year 2035 are starting their kindergarten year right now, folks. So kindergarten graduates will also be college graduates by the time 2035 comes around. And the reason that I start with this question is because what I'm concerned about most is how to prepare these kids for a future that we don't even know what it looks like yet, what exists, right? What technology are we going to be having? What environmental or social concerns are these children going to be facing when they graduate from college and join the working force? So I think the most important skills are things like imagination, creativity, and problem solving. Right? They're going to have Google or Bing or some other fact-finding source, right? They've got their tech. They can Google and find those facts. But it's going to be the critical thinking skills that these students are going to need in order to face this unknown challenge that awaits. So I'd like you to keep that in mind as we go today. And just a short introduction, an outline, if you will. Today I'll be talking about 3 different studies just to paint an overview of the type of work that I do. And I think a lot of them connect to your theme here of moving and making, so I'm excited to share these with you. And then I'll conclude by connecting back to that question about 2035 and how we might prepare teachers to help get our next generation of students ready. So this graph I always start with because it really sums up my motivation. Why do I do the work that I do? And if you can see on both sides, on the left-hand side, you've got just our US population in terms of race, ethnicity, gender, compared to on the left-hand side, the percentage of individuals who make up our STEM workforce. So who's actually employed in these STEM careers? And I'll give you a minute to look it over, maybe find yourself on there if you can. And I think you'll notice some discrepancies, right? Not equal if we look at who makes up our STEM workforce compared to who just is in our US population. And so to me, this signals that our educational systems aren't always equitable. They aren't always accessible to everybody. Or we might be seeing equal distributions on each side of that. So a lot of the work that I do is working with teachers who go into diverse schools, who work with diverse student populations, and who are trying to encourage them and excite them about STEM so we can shift some of those graphs that you see there. Another point I want to make, it's an exciting time in science education. Just show of hands who's heard of the next generation science standards. Awesome, that's good, my people. So science standards have recently changed. So in California specifically, we have adopted the next generation science standards. And when I was teaching middle school, I was following the old 96 standards, which if you recognize those or if you experimented with those, it's a list of facts, right? Students will know X, Y, and Z. And really what that ends up doing is teaching students to memorize, right? They have to memorize these facts to regurgitate them on a test, bubble in the right answer, and yay, right? End of the day. But these new standards are really asking us to do something different. And I think it's an exciting time. So what I've displayed up here are science and engineering practices. And the biggest shift that I see with our new standards compared to the old standards is that students are actually expected to do science now, or to engage in science and engineering practices. So things like asking scientifically testable questions, planning their own investigations, and analyzing their own data in order to engage in argument from evidence or to model natural phenomenon. And so now teachers are being asked to shift their practices. Instead of telling students what they need to know, teachers are supposed to provide opportunities for students to do these things and learn the knowledge for themselves. So it's a big shift in how we've taught science previously and where we're going now, but I think this is good signs for teacher education. So here's an overview of some of the bigger topics I'll touch on today, and I'll also conclude with this slide to wrap it all up. But here's what I try to emphasize in my work with teachers who are incorporating these new standards and, again, working with diverse student populations. First thing I'll talk about is research practice partnerships. So how can researchers like me not just be up in our ivory tower? How can we actually get down, work with schools, work with administrators, informal learning organizations to do research together, right? Research to improve practice. So getting away from this research and theory divide, instead doing it together. So that's a big component of my work. Another component, again, is community engagement. So in the examples that I'll share next with you, you'll see students going into museums and outside of a classroom to learn, because if you think about it, we don't spend all of our lives in school. We actually spend a very small percentage of our lives in a classroom, right? But learning is happening everywhere all around us. So how can we use our community resources to help our students and our teachers? And the last component is an expanded learning ecology. And I'm borrowing language there from Bridget Barron, who's a researcher at Stanford. But again, connecting to this idea that learning's not just in a classroom. Learning is everywhere all the time. So how can we be intentional, that's the word I'm trying to say. How can we be intentional, I can't say it again, intentional about connecting these formal and informal learning opportunities. So again, outside of the classroom and in the classroom. Okay, so I'll share a few different studies that I've conducted. The first one I like to call Making and Breaking Bones. Yeah, let's just dive in. So in this first study, I worked with a middle school science teacher who wanted to incorporate engineering design in her classroom. So our new science standards also, for the very first time, include engineering, which is exciting, but also a challenge for our teachers who have not taught engineering or have not experienced engineering from the standpoint of a learner. So this middle school teacher approached the university that I was working with as a graduate student for help doing this. She had what she thought was a pretty authentic project, but just needed help implementing that in the classroom. So her project that I helped with was working with a stunt double. So this was in Santa Barbara, which is not too far away from Los Angeles, California. So for the students in this classroom, one of their parents happened to be a stunt double in movies for the LA area. And you can actually see him here. And unbeknownst to me at the time, if you are missing a limb, as you can see here, he's missing the lower part of his leg. Apparently there's a niche in Hollywood for you. You can be a stunt double. I didn't realize that. But you can participate in action scenes and actually have limbs and other parts of your body blown up, and it doesn't hurt you, right? I didn't know that at the time. That was a fun fact to me. So one of the parents in this middle school classroom happened to be a stunt double. The teacher found out about it, and they started talking. And the resulting project that they came up with and gave to 7th and 8th grade students was to fabricate a bone that breaks with realistic fracturing when an outside force is applied. So these students were tasked with designing and then 3D printing the lower part of a leg that the stuntman could then put into a model, we can see there, and use it in a real movie scene. I don't know which movie scene it was used in for privacy concerns. We were never able to find out, but it was a fairly authentic challenge in the fact that the winning design was going to be used in a movie. So for 7th and 8th graders, that was pretty incentivizing for them. So I'll talk a little bit about the steps that these students went through in order to complete this design challenge. It really started in group work. Students created their own teams of 2 to 3 people. And they just started drawing. How are we going to create a bone that will break in a realistic fashion? After they thought they had a good 2D design, they turned to Tinkercad. Has anybody used Tinkercad before? Okay, a couple of us have. It's a great 3D software for beginners, I would say. So this teacher was using Tinkercad. It features a lot of drag and drop shapes that you can use, or you can design your own. So you can see students really had to think about how are they going to connect 2 pieces, or if they make it 1 piece, how and what angle and what amount of force would be required to break that bone. And then, of course, 3D printing, right? So students were, this was in 2013. I know 3D printers have come a long way since then, but at this time, it was very uncommon to have them in a middle school classroom. I think they're starting to become more common now, right? But back then, the students felt very privileged that they even had this source of technology available to them, and they got to use it for this challenge. So they went through this process a few different times. I think each group printed 2 or 3 prototype bones that they were then able to test. So we can see the stuntman is working here. So he came to the classroom several times to give students feedback about their designs and test. So I'll show you a video on the next slide, but we can see a couple of our 8th grade students testing with fake blood too for movie effects, right? So I'll share this video now. This was I think the winning design. So you can hear some oohs and ahs as students get excited. Just a short snippet just to show you the excitement, right? When the student is making something that they actually get to use and has a larger purpose, in this case going into a professional movie scene, they were quite excited about that. Okay. So that was the first study that I wanted to share. And I do have other slides. If you have questions about this, we'll have plenty of time at the end. So happy to answer any questions when we get to that point. The second study, I'm going to move us along, is again with middle school science and engineering, but a different population. So I like to call this study Fidgeting with Fabrication. And this was really a research practice partnership. So again, I was approached by a special education teacher this time, and he was interested in incorporating engineering. Again, this is a big new thing that teachers are having to do, and there's not a lot of resources out there for them to do this. So we decided to conduct this study together. So this teacher had noticed that his middle school students, specifically with ADHD, were struggling to stay still and focus in their classroom setting. Anybody have students or family members? Yeah, I see head nods. So ADHD. And especially in a middle school classroom, that can present some challenges, behavioral challenges. So his idea was to design and make a personalized fidget tool that these students could then use in the classroom setting. So this was a few years ago when these fidget spinners and all of these varieties were very popular. Do we all remember that? Not? Okay. And so I want to highlight here, though, while these spinner designs were very popular at the time, a fidget tool can take very different shapes. It could be as simple as just a lavender-scented stress ball, right, made out of Play-Doh that somebody can make. So we really pushed these students to think outside of the box and to design a fidget that was specific to their needs and their interests. So I've mentioned that engineering design is in our new science standards, but here's what it looks like if you haven't seen it. 3 main components of our engineering design process. First is just defining and delimiting engineering problems. So what are our criterias, what are our constraints and limitations that we have to keep in mind as we design? The next part B is designing solutions. So once you've identified your problem, what are possible solutions? Lots of possible solutions. And then you can optimize, right? Test those different solutions, see which ones meet your criteria and your constraints best, and optimize that one solution. So that's what we're having our teachers now do with our K through 12 students in science class. So to get back to the special education classroom that I mentioned, I'll walk you through our process. So the first part, again, was defining the problem. So I went to this middle school classroom, worked with the teacher, and only the students with ADHD participated in this study, but they were quite inept at telling me what their problems were. They knew that they were struggling to stay focused. They could tell at certain points in class when their attention would start to drift away. And so we had very honest conversations about what they might need. They all got their engineering design notebook, which they were very excited about, and started brainstorming. We talked about what would make a good fidget in a classroom setting. For example, one of the students said, well, it can't be edible because you're not allowed to eat in class, right? Which I thought was a pretty good thing I hadn't even considered before. Another student said it shouldn't make noise because that might be distracting to the other students in the classroom. And so they were very insightful about what they needed in this design. And then over the next 5 weeks, I believe I went back every week, we started designing. So we went from 2D drawings to Tinkercad again, and a lot of flexible seating, a lot of flexible groupings. It was very open-ended, so a lot of universal design for learning, if you're familiar with that slang. The exciting part, though, after students had their 3D designs ready on Tinkercad, an important note is that this was a very rural agricultural school in the foothills of Santa Barbara, and they didn't have a lot of extra money for things like 3D printers, unlike the last school that I mentioned. So they didn't have access to these tools, which was a problem, but our solution was to reach out to a local science museum. So there is a new science museum. It is called MOXIE, the Wolf Museum of Exploration and Innovation. It's in Santa Barbara downtown. If you get a chance to visit, I would highly recommend it. It is a physical science museum, but all of their exhibits are connected to these new science standards, and it's fun for adults and kids alike. So we took our students with ADHD on a field trip to this museum. It was about an hour away. We were able to get some bus funding to do that. But they had a designated makerspace or an innovation studio with the necessary fabrication tools for students to complete their projects. So you can see they've got a few 3D printers over there, they've got a fancy laser cutter and all sorts of other fabrication machinery. So students were able to go to this space and get feedback from the museum staff and use the tools personally there. So you can see our students there working in the innovation workshop with the museum employee. And this was great because, again, the school did not have access to fabrication tools, which can be a limitation, but there are a lot of spaces that are popping up. Libraries sometimes have maker spaces or fabrication tools, community centers, and so teachers can get creative about how they access that machinery if they don't have it. And then I'll share one example of a project that a student created. This student was a 7th grader, and what we can see over here on her first day, she drew a fidget spinner. She was really set on this fidget spinner design, and you can see she customized the spinner to include hearts and petals that gave you the appearance of flowers. All right, here we can see her first Tinkercad design. Shifted a little, but you can still see the hearts and those pointy stars. When she got her first print, though, her first prototype from the museum, it worked. The dimensions were accurate. It was as she had designed, but the stars were too pointy to spin. So we put her center bearing in and she went to spin it and immediately realized, hey, that's not gonna work. Those pointy stars actually hurt my fingers. So that caused her to go back to the drawing board, back to Tinkercad, and she redesigned. What I really like is you can see the similarities between her first paper drawing and her final green spinner. And she noticed that Tinkercad did not have pre-formulated flower shapes. So instead of that, she created the appearance of flower petals by using small hearts. So I really like this just because you can see the parallels in her final and versus her first design on paper. And this was just one of our students' work. Every student had a very unique story like this, but I think this one is one of my favorites. Pretty interesting design. So usually when I give talks like this, I'll talk about these projects. They're very authentic, they're very creative. The students had a great time, they made some cool stuff, but I get this question a lot. It looks like fun, but are they learning? Anybody want to confess? Did you have that thought while I was talking? It's okay. Well, I get this question a lot. How do you know they're learning? Or if I talk to principals a lot of times, they're like, yeah, it looks like fun, but why am I going to invest all this money in buying a 3D printer or training my teachers and sending them to these tech conferences, right? What's the payoff, right? The value added. And it turns out they're learning a lot when they're making things. And I'm not going to go into all of these results, but I've done extensive reviews of the literature, and there are empirical studies connecting learning to all of these things through the act of making. So math, art, writing, science, engineering, spatial reasoning, computing. So I'm going back to the 80s here. And so it turns out they're learning a lot of our more traditional subjects, right? What we think of as disciplines or subjects. And they're also learning a lot of things that are harder to measure. Things like creative competence, resourcefulness, self-efficacy. And connecting back to that question of 2035, I think it's these skills that are really going to serve our students the best, right? Can they identify what the problems are, and can they optimize and create solutions? So with that, I'll introduce my final study. And really the final study was my attempt to prove that yes, when you make, you do learn. So with that, the final study I'll talk about today is in the context of a pre-service teacher education course. Has anybody here been to a maker fair before? I know they're not, well, maybe they're coming back, I don't know. We got Make Magazine back, but there's some funding issues. But San Mateo for many years, I think since 2006, has had their flagship maker fair, which is great. A good community of just hackers, artists, computer scientists coming together, a lot of teachers and educators as well. And so we created a much smaller event modeled off the big San Mateo Maker Fair. But it was a maker fair for our pre-service teachers to get experience designing STEM activities and then facilitating them. So for our 36 pre-service teachers, these are pre-service elementary school teachers, which are gonna have to teach every subject, right? So making is a great way to appeal to multiple subjects at once. So we emphasized making in our methods course for these future teachers. And their final assignment for this methods course was to design and facilitate a science or engineering activity aligned to the standards at a maker fair for guests of all ages. So we invited the community, other teachers and schools, and most importantly, we invited the students that were in our pre-service teachers' student teaching classrooms, right? So if you're a pre-service teacher, you're usually student teaching during the day, going to courses at night. And so all of the students that they get to see in their daily practicum classes is what we call them at Santa Barbara, they got to come to the university campus and engage in a very fun night. So I'll show a very short video so you can get a sense of the types of activities that our teachers planned and our students got to participate in.
Maker fairs are celebrations of innovation. They are about engineering, science, art, and making. They're held all over the world, the largest of which attract hundreds of thousands of visitors annually. Our event is a school maker fair, which is a much smaller event that focuses on elementary school children. The primary facilitators are students in our teacher education program who are earning their elementary school teaching credential. In class, they learn about the science standards and work in small groups to design a station that they facilitate at the maker fair. They've designed stations about building boats, bird feeders, kaleidoscopes, Play-Doh circuits, cardboard pinball machines, slime, and more. We've also had UCSB and community groups show off their work in technology, and children participating in GGSE-based outreach programs display their work. We then invite all children and their families in the student teachers practicum classrooms to attend. Both last year and this year, we had around 400 guests, children, parents, and teachers. Parents report that they love seeing their children so engaged in the activities. Teachers report that they use the activities they see at the Maker Fair in their own classrooms. And most important is that the student teachers report learning that children are natural problem solvers and more creative than they expected. They will go on to teach children in classrooms all over the state, and this experience will help them envision new ways of approaching science and engineering.
So I think that gives you a sense of some of the activities that teachers planned. But again, this was part of my dissertation research. So what I was interested in was the interactions that were occurring between these students, children visiting, and our pre-service teachers. So what I did was I had 3 different pre-service teachers wear point of view cameras. So they're very similar to GoPros if you've played with those in the past, but a very small camera that sits on their shoulder. And the teachers facilitated just as they normally would. They designed their activity ahead of time, wore the camera at the event, and just facilitated. What I did on the back end was to analyze the facilitation strategies that they used. How did they engage the children at these stations? And also, what were the indicators of learning? Again, I was interested in showing that learning was occurring at these types of activities. So I was interested in the interactions therein. And what emerged, what was the most interesting salient story was, I call it a tale of two stations. So I'll walk you through these two very different stations now. On your left-hand side, you can see a station where students made slime. Has anybody here made slime before? Yeah, or maybe you've had your own children, students make slime. Pretty popular. So the way that these teachers structured their slime making activity, you can see pretty clearly here. They had everything pre-measured and very organized step by step, so students could not make any mistakes. A child would walk up, they would grab a mixing bowl and a spoon, then they would be ushered to the next step where they would add their glue, the next step where they would add their borax or liquid starch solution. And then they got to the decorating part, maybe some food coloring or glitter. And then at the end, the teachers asked them, do you think slime is a solid or a liquid? The students would usually say, it's somewhere in the middle, right? And they would get a little pat on the back and good job, you learned something, move on, right? Not to say that every student did not love making slime, but as I'll show in a minute, there wasn't a lot of critical thinking going on there, not a lot of testing and devising their own investigations. So I want to contrast that to another station, which was about magnetism. The teachers had 4 or 5 different activities that students could engage in, but all centered around the concept of magnetism. Students could approach and start at any of these small mini activities. And really the teachers greeted each student and asked them, what do you know about magnets? Keep in mind that it could be a kindergarten student who was talking to them, could be a 6th grade student, or it could be a parent or grandparent, right? But these teachers usually started, what do you know about magnets? To elicit some initial ideas before directing the student to what activity they thought would be best. So I'll talk more about these. In graphical form, here's our slime station though again, right? One path, one way, no room to make mistakes. Really no room to question, just answer solid or liquid. And I want to contrast that to the magnetism station. So again, a student could start at any one of our activities. So I have a video that I'll show you in a minute of a 1st grader engaged in some of these. But one of the activities was just magnet wands, just what is magnetic, right? So they had just a pile of junk, some magnet wands, and students just got to play and see if anything was attracted to their magnet wand. Another one is a pretty famous one in elementary school classrooms. They have a center rod and you have to make magnets hover with enough distance in between them. They also kicked it up and included copper, which copper is a metal. So a lot of children would assume that it's magnetic, right? Most metals are magnetic, but copper is not magnetic. And copper does some interesting things when you add magnets to it. Eddy currents, if you're familiar with that phenomenon. And I'll show you a video in a minute to demonstrate that. They also had a magnetic pendulum and the ability to make a motor with some simple materials and a magnet. Also really important to point out here is the teachers had a designated stop and think area. So if a student got to a point where they got stuck or they couldn't articulate something that they were observing or watching, the teachers would direct them to the stop and think area so students could draw or write what they thought was going on, which was a good source of kind of a formative assessment for the teachers, right? They could see what the students were getting and then redirect their investigation from there. So I had to turn to work done by the Exploratorium Tinkering Studio. Has anybody had the opportunity to visit the Exploratorium, San Francisco? Okay, so the Tinkering Studio there is wonderful. And they are doing some research right now on learning in more informal tinkering style settings. And so I had to use their learning dimensions because there wasn't anything really capturing what I was interested in as far as formal classroom and formal research was concerned, formal classroom research. So these were the dimensions of learning that I looked for in my point of view video camera. On the student side, were they showing initiative and intentionality? problem solving, critical thinking. Again, these aren't just facts, right? But these are more critical 21st century skills, sometimes people call. Again, the things that I think are going to be most important for our future students. I also looked at the teachers. What were the teachers doing? How are the teachers engaging these children? And I, again, used work done by the San Francisco Exploratorium. This is their facilitation field guide. And this is how the museum staff are trained. So first, they need to spark a student's interest in some activity or phenomenon, a demonstration. Then they need to sustain it and then deepen it. So I was looking for things like supporting process and moments of failure or frustration. What did a teacher do if a student got stuck, right? Those were the types of questions that I was really interested in answering. So I mentioned my video cameras, my point of view cameras. And I went through an iterative process. We had a whole team of undergraduate researchers who were trained to go through this video with me. And the Exploratorium is great. They have a whole video library that you can get access to. So you can see how they are categorizing things like problem solving or critical thinking or creativity. So we were able to compare our video directly to the video from the Exploratorium for consistency's sake. So I'll share some of the results now, starting with the teacher's facilitation strategy. So I'll give you a minute to look this over, but what we're seeing, Miss Sarah, green slime, compared to Miss Maggie, the magnetism station is shown in blue. And this is just the facilitation techniques or strategies that we coded for in our video analysis. I'll draw your attention to a few different things. What stood out to me most apparently was the instances of direct instruction. At the slime station shown in green, students were most often told what to do, right? Grab your mixing bowl, add your glue, mix, add some food coloring. And so there wasn't a lot of interaction, but I mean, it was mostly direct instruction, right? Teachers telling the children what to do. Compared to the magnetism station, there was a lot less of that. Another thing, questions. This is interesting to me. So it came out almost exactly equal. They were asking questions of the same rate at the magnetism station and the slime station, but the types of questions they were asking were drastically different, as I'm sure you can imagine. So at the slime station, it was a lot of, do you already have your water in there? Have you mixed that enough? Do you need more glue? Versus the magnetism station, what do you think is going on here? Why do you think that's happening? What's causing that to happen? And so the types of questions were drastically different across these two stations. Another thing engages with observations. So this is something that the Exploratorium recommends, is to talk about the observations, whether that's a student work sample or an investigation that they're going through, but to ask students to vocalize their observations, scientific observations, right? And that happened a lot more frequently at the magnetism station, where students were designing their own investigations, right? Can you get that magnetic pendulum to move in the way you want? Can you design this eddy current investigation to get the type of data that you need to answer this question? So very different there. And then one more thing I'll highlight here is just the encouraging and the celebration. So slime, it was a factory line, right? It was just get them in and get them out. Compared to the magnetism station, where students stayed on average 8 to 10 minutes longer. And there were a lot more moments of celebration, right? If a student figured something out, there was excitement there. The teachers engaged with them on that level. So very different types of interactions. So now let's look at the learning. So looking at the children now, down here we can see those indicators of learning that I showed from the San Francisco Exploratorium. So again, things like creativity, problem solving. And you can see the blue, magnetism, versus the green in slime. And the way I would recommend reading this is, for example, that conceptual understanding. Every child who visited the magnetism station showed, on average, 4 instances of conceptual understanding, compared to less than about every other kid at the slime station showed an instance of conceptual understanding. So that was the largest difference. Are they understanding the science, right? The science of magnetism or the science of non-Newtonian fluids in the case of the slime. So that was very drastically different. And then another thing that stood out to me, I'd like to highlight here, around this initiative and intentionality. Slime and magnetism, there wasn't a huge difference there. But again, the students showed initiative very differently at these different stations. So in the case of the slime station, students showed initiative by asking if they were doing things correctly, right? Is this good enough? Do I need more of this? Is this right? Is this correct? That was how they were demonstrating their initiative. Compared to the magnetism station, it was not confirmatory at all, right? They were off doing their own thing, designing their own investigations. So even though slime did have quite a few numbers of students showing initiative or intentionality, it was very different again than we observed at the magnetism station. And I didn't include this here, but this is a significant difference between these two if you're a quantitative stats person. So to sum it up, if you conceptualize learning in these dimensions, students learned more at the magnetism station, statistically significantly more than at the slime station. So to sum up, if I had to give recommendations to teachers, which I do all the time, I share this type of advice with them. Open-ended challenges without one correct answer, magnetism, resulted in more diverse facilitation strategies, which resulted in more indicators of student learning. Okay, how are we doing on time? Okay, you want to watch an example? Okay, so I will share with you a video of, I call her Gabby, that's her pseudonym. She is a first grade student, or she was a first grade student at the time this video was taken, who self-admitted she was not a fan of science. She was a big fan of art and theater, not science. But I'd like to show her engagement at the magnetism station. So I have two very short videos. Let me check my timestamps. Okay. Okay. I should also point out that the teacher is wearing a point of view camera and she turns a lot. So if you get nauseous or motion sickness, you might want to divert your eyes. I apologize. You can probably imagine our frustration when we were analyzing that video on the back end. So Gracie is the little blonde girl with the pigtails and the cheetah print dress. Yep, here we go.
And number 11 is very careful. This is a copper one. And pennies are usually what happens here. Copper doesn't stick, so what do you think is going to happen when we drop this down? It's going to fall right through. Be careful. I want you to look carefully, okay? Look carefully. What's happening? I think it might be easier for you to do a bigger pipe. So let's do that one. What do you think is happening now with a bigger pipe? What's happening? Can you explain it? Can you explain it with the seat to your mom so she can't see over here? What did you do? Why don't you go shower? Let's go shower.
I'm gonna pause it there. There's a lot going on there, I know. A couple of things I'll highlight. This teacher, she modeled changing a variable. Did anybody notice that? She had the first copper pipe, and Gabby was dropping the magnet down. Does anybody have a prediction what you would see if you dropped a magnet down a copper pipe? Has anybody done that before? Yeah? Well, what would you see? Put you on the spot. Yeah, it goes slower. It's an eddy current phenomenon, and it almost kind of like circles down like this, much, much slower than you would just expect if you were dropping it outside of a copper pipe. And so that's a hard thing for a first grader to explain. That's way above standard for the record. But this teacher was asking this first grade student to try to explain it. When she got stuck, she brought in the girl's mom. Can you go explain it to your mom, right? Maybe she can't see over here. Let's go talk to your mom about this. So that was one of the facilitation strategies we coded for, pulling in outside observers or getting other people involved in the conversation. So I'm gonna jump ahead to Gabby's investigation, 1425. Okay. So Gabby has played with the copper pipes a couple of times, still struggling to articulate what's going on. And you'll see now she moves on to the magnetic pendulum activity. The pendulum also has some copper, so there's a connection between the copper pipes and the pendulum, which you'll see next.
Second, I have one more thing with copper if you wanted to test it out on something different.
If you want to leave that with me, go with Miss Mendoza over there.
So this is also a magnet, and this is just a big old stick of copper. You're gonna test it with this. No? Neither side. Do you want to try to swing it and see what happens? Okay, it looks like it's swinging pretty well. How long does it swing for? Can you swing for a long time? I'm sure it's safe to say we're swinging for a really long time.
Here, put this one
What
back
if we
over
put
there.
this big old pile of copper on it? What happened to the pipe? Well, I heard it slow it down. Yeah. What do you think would happen to the other side? I don't hold a chair over it. What happened? Things happen.
That's controlling for variables at a first grade level.
Still slow it down. All right, careful. Well, didn't you say it slowed down over here? That's what she was just telling. Now it's slowing down over here.
That face, that face. If I could get every one of my students to make that face, I know I'm doing my job. So she is just a very illustrative example. I saw lots of children, not quite as expressive, but going through similar processes, right? Testing, revising, taking ownership, right? She took control of these copper plates. So wait. I just want to make sure these are flat, right? That could mess up the experiment. Earlier, she took a stick of copper and she tested both sides along the magnet to make sure that they were behaving in the same way. And then she played with the speed that she swung the pendulum, right? Wait, I'm gonna do it really, really fast now. And she applied more force. Again, she's a first grader, but pretty good explanations and testing, great controlling of variables, higher than the next generation standards are asking for first graders. So pretty great example. Okay, PowerPoint. Okay, so I do have an activity that we could do. I was going to give you each a type of learner, a description, and something we're trying to get them to do. So a practice, a learning practice. And in my envelopes, I have facilitation strategies from the Tinkering Studio, but maybe we go until 6, is that right? So do you want to play a game? Yeah? Or more time for questions? That's kind of where we're at right now. Any preferences? Game? Show of hands. Okay, that was enough for me. So I've got 5 different envelopes. There's different facilitation strategies in them. We might have to get into groups. There's one here, one here. The 4 of you perhaps be a group. And then there's my last envelope. Yeah. So take them out. You can spread them out on the table. But if you were trying to get the observer to inquire, What facilitation strategies or combinations of strategies might you use? And hint, there's no one correct answer here. But a student who's an observer doesn't really like to inquire. So if you have a student who really likes to observe, just kind of hang back and not really get involved, how would you get them to ask questions? How would you get them to engage? Somebody doesn't like asking questions. How are you going to get them to open up? Then I'll ask you to share out your facilitation strategies in a moment after you've had a little bit more time. You can see if groups agreed or disagreed. Any ideas here? Oh, it's like, oh, be patient. Yeah, think out loud. Yeah, those are great ones. Take another 30 seconds or so. Let's see if you can get a facilitation or strategy too that you wouldn't mind sharing out. Okay, folks, does anybody feel confident in their facilitation strategy? How would you get the quiet observer to open up a bit? Maybe ask some questions. Any strategies you would recommend out there?
We chose one of them, grant permission to be silly.
Oh.
Maybe they're an observer because they shared something one time and someone laughed, or, you know.
Yeah, definitely. Yeah, I like that. Encouraging them. Yeah, through modeling being silly yourself. Yeah, definitely. That's a great one. Any other strategies out there you think would work well for this situation?
Be patient.
Yep, definitely be patient. I heard ask why 20 times, a couple times that came up. Be patient and keep asking. Great. Anything else you feel would be helpful in this situation?
Inquire about their process.
Yes, that's a big one. So ask them to talk you through that, walk you through that. What does that look like? Great. Okay. Want to do one more? Okay. Next one. The lone wolf student who likes to work on their own, how would you get them to seek and share resources?
That's a good one.
Yep, it's a good one for this type. Oh, just like that. Oh, yeah, similar. Lone wolf. Yeah, definitely. Anybody willing to share out some of their facilitation strategies? Heard a couple good conversations.
We were thinking two of the ones that we put up or asked them to ask another or ask them to teach another so that they're expected to communicate.
Yeah, definitely put them in the role of the teacher. Yeah, definitely. That's a good strategy for the lone wolf. Any other strategies out there you'd recommend?
Dare them.
Ooh, I like that. Can you say more about that? How would you do that?
Well, I mean, they feel very confident. So, I mean, if they're very confident, but they don't like to work, come on. I want to see if you can actually do it with somebody else.
Challenge them like that. Yeah, definitely. With the right student, I could definitely see that working. Yeah. I bet you can't. Bet you won't. Yeah, yeah. Prove you wrong as the teacher. Yeah, that's a good motivator for some students. Any other strategies you'd recommend?
I think this one of be the devil's advocate. Again, depending on the student, could work, especially with this piece of recognizing your own not knowing. Sometimes you need somebody to kind of prompt you toward that, saying, I think differently, or maybe not in every case that does that work. So.
Yeah, poking holes in their theories, finding the gaps in their understanding. Yeah, absolutely. That would be effective as well. Well, thanks for playing, folks. I borrowed this from the Children's Museum of Pittsburgh. They also have a big maker program, and this is one of the activities that they use with their museum staff and teachers that they come in for professional development. So thank you for playing. There's also learner type and learner practice cards available online for free if you want to use this in your own professional development or work with teachers, facilitators, etc. And then I'll give you another minute to finish putting in the envelopes. You're welcome to keep the envelopes if you need them. I don't need them back. So thank you for playing. We could have done a few more rounds of that. But the point being is there's a lot of different facilitation strategies out there. And depending on the type of student and depending on the outcome or the learning goal that you're going for, different strategies may be more or less effective. So I promised you I would return to this slide and we'll wrap up after this and should have plenty of time for you all to ask questions. But this is my model. This is what I think it's going to take to reimagine science education or science teacher education, depending on your lens. Really, it's going to take getting involved with practitioners, so working with teachers, working with administrators. So in the examples that I shared today, we had a research practice partnership with a science museum and multiple middle school teachers, right, where we engaged in research together. It wasn't just me going into their classrooms and studying them, but we designed the study, collected data together, which is very different than a lot of other studies, traditionally speaking. But it gives these teachers an opportunity to be recognized, right? To go to conferences, to present, to publish in Science and Children and other NSTA press journals. Gives them a chance to contribute to their fields. Community engagement, again, I only talked about really a museum in this case, but that added a lot of relevancy and authenticity for our students. The fact that they got to go to this new museum, work with this new technology, to design something personal for them was, I think, the most important part. That was the exciting part for the students. So that community engagement. And then again, all of these examples that I shared today did not just happen in a classroom, right? With desks and rows and one teacher at the front of the room, right? These were all different ways of engaging outside of a formal setting. And so for our teachers, right, who are going to be working with diverse groups of students, I think they need to see these expanded learning ecologies in action. So that's us taking them out of their university classroom and bringing community members onto our university campus, having an authentic assignment where they facilitate at a maker fair for guests of all ages, was really an opportunity for them to see sense making, right, across ages. They got to facilitate for a kindergarten student, 6th grade brother, and their grandparent all at one time, and had to find a way to get all 3 of those very different learners engaged and to stay engaged. So this is what I'm trying to do at Fresno State. Most of the examples I shared here were from UC Santa Barbara, where I did my doctoral work. But now at Fresno State, I have created a research practice with the Fresno Discovery Center. Has anybody been there in town? Yes. So they got new leadership about a year ago, and we've been doing strategic planning. But next semester, I'm going to be bringing my pre-service science teachers out to the Fresno Discovery Center to do similar activities, design new curriculum for their field trip programs, their summer camps. So continuing this work, even though I'm in a new community now. And with that, I'll wrap up. Thank you so much. And I'll take any questions now. Got plenty of time. It's a small group, so.
Hi. I'm interested in in that graphic that you had before with the community engagement. You talked about that being a big piece, and with the example where you had the special ed class or middle school in the rural district and connecting up with the museum. How did you initiate that relationship? Or do you find that, are there any best practices that you have? And was that a one-shot deal, or did you try to encourage a continued partnership between the museum and that school?
Yeah, great question. A few different things. Most of the work that I've done is connected to teachers. So I used to be a teacher. I'm married to a teacher. All of my friends are teachers. And so when I think about working with a new school, I always go to the teacher first. A lot of people will talk to the principal first, but I have found that if you get a teacher that's excited to work with you and wants to work with you, they can convince their principal, right, for anything. So I tend to target the teachers, kind of the ground level, so to speak. And in the case of the special education classroom in the museum, that was an ongoing partnership. So I described one project here, but they did have a couple other engineering projects. And that museum, I've worked with other classrooms as well. So the museum was a central place, and I pulled multiple teachers into the museum before. So yeah, I think starting with the teachers is the best piece of advice that I have. And again, it helps if you're a teacher. I think that I know their language, I know their struggles, I know what their daily schedule is like. So that's allowed me to build rapport and I think relationships, which is essential in these research practice partnerships. You've got to be working together on the same mission, on the same goal, and very aligned. So I think my experience as a teacher has been most helpful. Did I answer your question? Were there other aspects that I forgot? You talked about how to get started, maintaining.
What about the other end? Like, so the teacher, but then what about the other, like, partner?
Oh.
The museum or that, how do you?
Yeah, that's a good point too. Usually in my experience, these informal learning spaces are dying to like collaborate with researchers or schools. So in the case of the Fresno Discovery Center, I just emailed the director, hey, you've got this great informal site. I'd like to come check it out. And that was the conversation starter, right? And after that, I was invited to be on the board a few months later, and now I'm in their strategic planning meetings. And so it was really my initiative, I think, that started that. And the same with the museum too. I heard about this great museum. I knew somebody who kind of worked there, so it kind of got in that way backdoor. But really it's been a lot of me initiating these things, but not a lot of people saying no, right? If I'm there offering to help and offering to work with these people, there's usually been very positive, productive relationships as a result of that. But good question, yeah, that's a very good question.
If we want to be involved in like the maker fairs or being part of training pre-service teachers, how do we go about that?
Oh, we should have lunch together. No, there's a lot that we could do. Honestly, the makered.org is a great resource. I don't know if you're familiar with that. Maker Fair is run by Make Magazine, but they have a nonprofit they've created called makered.org, and there are phenomenal resources on there. Just lots of different project ideas, ways to get started. They've got how-to guides, how to plan a maker fair, how to do these own events. So makered.org is a great resource. I also always am on the Tinkering Studios website. They are posting new projects all the time. They even have these things called NGSS snacks, which are short, fun science activities that are connected to standards. So the Exploratorium Tinkering Studio is my go-to website for projects and things like that. But yeah, I honestly, now that I'm at Fresno State, I am a science teacher educator and in charge of increasing the number of science and mathematics teachers just across the valley. So if you are interested in contributing to that, I have tons of business cards and would love to speak with you on a more ongoing basis. You know, I can give you all the links and resources that I use, but I think a personal conversation and figuring out how we can work together is even more productive. So yeah. Did that answer your question? Yeah. Great. Yeah, definitely.
I have someone online who has asked a question. Says, I love the comparison of EDI versus discovery-based learning through the slime and magnetism stations. I'm curious how you decided how a moment qualified to be coded as a conceptual understanding or each of the other categories you were looking for.
How I decided a moment to be coded. So that's a good question, methodologically speaking. It was a challenge. It was not easy to do. We started with the Tinkering Studio's video library. So the Tinkering Studio created these categories. They collected their own video of students engaged in activities, and they had their own coding process. So they had an example. This is creativity, for example. And so we were able to compare our video data to the Tinkering Studios to compare, to ensure that they were comparable, right? And that we were coding things in the same light. But that wasn't enough as video data is actually becoming more common in informal learning spaces. A lot of museums are using video data now. And so there's a lot of literature about how to separate and what do you classify as a moment, right? Where does that start and end point go? So there's a lot of research out there, a lot of people who've done more thinking on this than I have. So we really researched and referenced the literature in that regard. But we also had a team of researchers doing this, right? So it wasn't just me isolated, okay, I've decided this is initiative, this is problem solving. So we had a team of individuals. Before the team met, I spliced things according to moments. So I defined a moment as a conversation between a teacher and a student about the learning outcomes, so magnetism or states of matter. And so I created that start and end point, like the stop and the end. That's what a moment was. And then once we had our moments, then we could bring in extra researchers to ensure that we were viewing things in the same light, according to that Tinkering Studio video library that's available. So it was an iterative process. Each coder, rater, whatever you want to call them, would take their moments, go home, do it individually. We would come back together as a team, and we would go bit by bit and talk about the facilitation strategies as well as the indicators of learning. So teamwork, lots of reference to the Tinkering Studio, and reference to the literature, how other people have handled video data. There's a lot of good work out there. So hopefully that answered. Yeah.
So did you
Follow
have
up?
more than one coder?
We had 8 coders. Yeah.
They looked the same video clips?
Same.
So you
Same.
got an average.
Yes, yeah, absolutely. And we used consensus. So if there was disagreement in our team discussions, we hashed it out, right? We didn't just move on. Well, why are you seeing this? What is your evidence? How do you support that? And that was where the teamwork was really essential to ensure that we could reach a consensus on those coding decisions. It's a good question, though. Got lots of resources if you want to read more about video coding.
I have a question, or at least a comment. In the video that you shared of the copper and the magnetism, I thought it was interesting to see the point at which the child posed her own problem. And you probably didn't see much of that in the slime activity because it was sort of step by step. But I thought it was interesting to see that even though there were materials and there were maybe some suggested activities, that the way that you had created that
space allowed for that problem posing, which is sort of asking your own questions of, I wonder what would happen if, and then she started to rearrange the copper on the chair. So I think it would be interesting to sort of look for those moments and code those sort of, when does the child pose her own problem in that activity? And then how does she, what's her methodology in sort of answering that research question that she poses? How does she make sense of it? What tools does she use? When does she ask for help? Because I think that's another one of those, getting back to your 2035 introduction of, you know, will we continue to pose our own problems? Will we continue to think about the things that are happening? So that's just more of a comment of something I would find interesting. But then I have a question too about, you know, much of your work seems to really try to bridge that informal and formal learning spaces. And do you see challenges in that work in terms of, is classroom learning ready for making? Are schools ready for making? Is making better suited in the informal world? Or are the principles of making suited for classroom learning, but the actual making itself, it takes a long time to print something on a 3D printer until that improves. But what sort of, I guess the question is really, what sort of challenges or barriers do you see in bridging those contexts? And are you finding traction in some of that work?
Yeah, I would say that formal classrooms are long overdue for making and these more student-centered instruction principles, right? But you're right, when you take a project like I'm going to go to the bone example, 3D printing bones, right? And you put that in a classroom setting, challenges do arise. First and foremost, the one I hear most often is assessment, right? How do you know that they're learning? How can you show that they're learning? And usually that's voiced from some teachers, but often administrators, right? How are they going to do on that standardized test though? That's what I see is a huge challenge to more open-ended projects in traditional classrooms is assessment. How do you demonstrate that learning is occurring? My response to that challenge is usually along the lines of portfolios, right? A lot of our, like MIT, for instance, is now accepting digital portfolios instead of like GRE scores for graduate programs, right? And so these leading universities are starting to go away from standardized tests to more portfolio-based assessments. So that's usually what I share with administrators who are worried about assessment. If a student can demonstrate how they made something, why they made something, then why it's important, I think that's more valuable than any bubble they could fill in on a standardized test. So assessment's a big area, a challenge. Another challenge that I see is just time. So you mentioned like 3D printers take a long time to print, right? And with 20 or 30 students in a classroom, right, that is going to be a limitation. So I have found teachers come up with really creative solutions for that. But a lot of it is falling on the teacher doing extra work, right? The teacher staying late and doing these prints or finding the right library or community center who has help, right? So I'm still working on that challenge, just how to facilitate it. Honestly, I'm not a big fan of subjects, right? Science class and math class and reading class, right? If we can start to get rid of those silos of disciplines and start integrating across classes. So maybe you have your math class and your science class, but we're doing a joint project and that gives us block periods. And then all of a sudden you've got more time in a day to dedicate towards a project. So there's creative solutions. It's not always easy. And like I said, more traditional schools will push back on those because it's just so different. So assessment, just time management. What are some of the other challenges? Old school teachers, teachers pushing back and saying, no, this feels different. No, I don't know the technology. So teachers have to be willing to not know, right? And to be okay not knowing. You know, when I through Tinkercad to these 8th grade students, I thought I knew Tinkercad, but then they found all sorts of new tricks that I didn't even know existed, right? So these students are quite tech savvy. They take to this very well, but a lot of teachers who maybe didn't grow up with this type of technology push back, right, for fear. It's something new, it's something they haven't done before. So overcoming that is something I'm still learning how to do. But I think a lot of times if you engage teachers as a learner, right, from the standpoint of a learner, and they have opportunities to use technology free from assessment and pay cuts and pink slips and all that, that's where I see the most benefit coming with our teachers. So a lot of it goes down to teacher education for me and teacher professional development. How do we ensure our teachers feel comfortable using this technology and comfortable maybe not knowing all of the answers? Because in open-ended challenges like this, you can't always anticipate what your students are going to come up with at the end, right? That bone project, that teacher didn't know how the students were going to do this, but she did it anyways, right? And so I think being okay to fail and persevering, and teacher ed, I always go back to that. So I don't know if that answered your question, but yeah.
But that boils down, that's what it boils down to, teaching teachers who've been taught to be fearful to become fearless.
Yeah, absolutely.
Right.
Said it better than I could have. Absolutely.
And that's the crux of it.
Yeah, it is. It is.
I mean,
This is more follow-up on the what you were just talking about, especially with the issue of time. I'm teaching STEM classes in middle school right now, and one of the things that I've found out the last couple of years doing this is the logistical demands of having this equipment, having the 3D printers, which do have filament jams, which have to be recalibrated, having robotics kits that have to, you have to make sure all the parts are there, and all of that kind of stuff. So it's not just like getting the printing done, which is, yeah, you said it, going in on Saturdays, staying late, you know, running the printer whenever you can to get things done, but then taking care of all of that stuff that you really can't do when the students are in the classroom anyway, because you've got to be doing other things when they're there, but taking care of all of the nuts and bolts, so to speak, of all of that. So.
Yeah, I've seen some teachers use student assistants really well in that regard though, right? If you have a few students that are kind of leaders in the tech or they really take to that, have them come in and set it up or train them to fix the filament. I mean, it takes a little extra work, but if you get a few students trained in certain things that happen a lot, that's been a strategy I've seen a lot of teachers use effectively too, for what it's worth.
I'm hoping to get there.
Yeah, no, it takes time. It takes time. These are big changes we're talking about here.
Time for maybe one or two more questions.
I answered them all.
Well, thank you.
Yeah, thank you. It's a pleasure.
Well, I hope that you've been inspired today as a maker, perhaps, as a teacher, as a learner, as a partner in ongoing work. If you're thinking about research, you've seen some great qualitative methodology today to think about how to get at what's being learned and how children and adults are engaging in that process. Also looking at some of the important cognitive and social aspects of learning as we've been exploring in this colloquium series, to think about ways that we engage in learning together in community through social interaction, but also the cognitive processes that are going on as we interact with materials and with the things around us. So hopefully you found something today that really inspired you in some important ways. And thank you for being here, for your participation. Hope you have a wonderful rest of the night and the fall season. We won't be back for our next colloquium until the new year, so you'll get a schedule for our new series in the spring. Until then, thank you for being here and fare thee well.